Hello, Miss Umpavles. This is Will, your old friend. I'm making a little video about two sample tests, all of Unit 9, why it's important, what we use them for, and I just want to show off some of my knowledge that I got during the unit, after the unit, show some understanding. So, we're going to run right into this thing. I'm hoping that my iPad setup is working. If not, I'll figure it out. So first, the bread and butter of this unit is going to be our two-sample z-test. Now, why would anyone ever need a two-sample z-test? It's really to find the difference in, probability between two populations. So if I were to say like, oh, what is the proportion of Glenbrook North students with hair over a foot long versus the proportion of Glenbrook South students with hair over a foot long? We would find those individual proportions and then see if there's like a statistically significant difference between those proportions, because our null hypothesis, we assume that they're going to be the same. And then with the confidence interval in this, so that first part of like, is there a difference? Is this difference statistically significant? That's our difference in probability between populations. But finding if there is a difference and where that true difference is, where the true is, that's where we get our confidence interval. And that's what the confidence interval is useful for. So that's why if there's like a 0 in a confidence interval, it's like, ooh, we can't say with that amount of confidence that there is a difference, because it could theoretically be 0. It falls within the, confines of our confidence interval. And then very similarly with our two-sample t-test, we're looking at the difference of means. So assuming that the populations are alike, what are the odds of us getting two different means like this? And if, let's say the mean number of 4.0 students in AP Statistics class at GBN versus GBS, if the means are significantly different, not mean number of 4.0, it's like mean GPA. If those two means are statistically, we're looking if there's a statistically significant difference between those. And that's kind of like what the t-test itself is. And then in terms of like where we get our confidence interval, it's like where that difference is. So our conditions are going to be pretty much across the same across both tests and our difference test, which I'll get to later. The first, always normal. So this is for our z-tests. We're making sure that the number, or like the population, times the probability is greater than 10, and n times 1 minus p is greater than 10. Pretty standard. It gets a little different for our means and our t-tests. We want to check first if it's stated, then if our population, or like sampling population, is greater than 30, if our sample is greater than 30, and if the graph or dot plot just don't show irregularities, could slightly indicate that it's normal. We really want to perform these tests, so we're going to go through all three of these measures and try and find a way to perform. Next, we want our randomness, either in the assignment of treatment or of like selection from the population. And then independent, always important. This is going to be our 10% condition, but you do not need to be independent if you are an experiment. So I'm just going to add that to our video. Do not need. Yeah. So let's break down some equations. First, confidence interval for the t-test. We have our first proportion minus our second proportion, and theoretically, if it's perfect, it should be 0. It's not going to be. Plus z square root P1, 1 minus P. You get it. We're looking at this part. This is going to be like our deviation, and this is going to be how many of them? So there's going to be a difference between our confidence interval equation and our our test against alpha. So when comparing to alpha, we want to do something called p-pool. Why would that be? What's this difference in equations from? So why p-pool? It's because our null hypothesis is that P1 equals P2. So why do we use p-pool? I had to redo, I confused myself with my own mathematics. Well, it's because we know that we can add like fractions. So if we have 2/8 and say 4/16, we know that this is just adding, 0.25 plus 0.25. We're going to get half, 0.5. But since we believe that P1 is equal to P2, just as this, we could even call that P1, and this are equal, we can add them across. So that would be like 0.5 as well. So that's why we're using a p-pool, is we're allowed to because of our null hypothesis. So we're going to have the confidence test equation of z to get our z-score. P1 minus P2 minus 0 over the square root of all this jazz. But what's really important to look at here is in our standard error equation, we have p-pool. Moving on to our t-tests. So pretty easy confidence interval stuff. We have x1 minus x2 plus or minus t square root standard error 1 squared over population 1 slash sample 1, s2 squared over n2. And this is going to find us where that true difference in means lies. And similarly with the t-test, we're going to find the probability with a t score, like what are the odds. We're going to use this t-test to get our p-value. We're going to use that to get p so we can find what are the odds of getting these two differences when we've assumed that the population means would be the same. And just really important to note really quick, excuse my bad drawing, it's important to remember if you're doing a two-sided or one-sided t-test. And, I should probably mention degrees of freedom. It would either just be n1 minus 1 equals this, or n2 minus 1 equals df. You would pick the smaller of these numbers. So let's say df1 is greater than df2, we would pick df2. And that's just to give ourselves as much error as possible. Really, you just want to use your calculator to get your degrees of freedom here. And finally, moving on to the last test of the unit is our matched pair t-test. These are our equations. T is equal to sample mean minus 0 over, or T is equal to the mean differences minus 0 over the standard deviation of the differences, square root of n. And that would be number of differences. So this test is really important because say we're dealing with some huge number. Let's call it the weight of ships. I was looking at some boats, military boats online because I find them interesting, giant cruisers. But they can weigh 50 million pounds, right? So in most statistical tests, a difference like this between two numbers like this, that's gonna not give us a big p-value. But if we take the sum of these differences and then do it, that's really what what's gonna determine if there's a statistically significant difference. Not difference in means, but difference in like totals. And what the standard deviation of those differences is, and if that's like normal behavior or if something's abnormal, and whether we have to reject the null and conclude the alternative, or what we're going to do, or accept the null. We don't accept the null. We just say we don't have, enough knowledge to reject it. But that's pretty much what we're doing in this unit. I hope you enjoyed.